Okay, in today's lab, we want to use lattice-Boltzmann model to simulate the forces on an aircraft wing. In this simulation, we will study how boundary conditions work to model fluid dynamics in lattice-Boltzmann models. The simulation code can be downloaded from this link here. This implementation is an extended version of the code discussed in lab 7. After some initialization, as we can see here, we have a function obstacle. This initialization step have been discussed earlier in lab 7. Function obstacle here create or simulate or model an obstacle at the middle of the simulation grid, which is an airplane wing in this example. We will further discuss this obstacle function later on in this lab. Here, we apply the no-slip boundary condition to the cells around the wing obstacle in the collision step. As discussed in the lecture, the particles bounce back after colliding with the obstacle, where each distribution component is replaced by the value of the component with the opposite velocity state. We can obtain opposite state using the non-slip non-slip array initialized earlier in the initialization step. The boundary condition at the inlet on the left-hand side of the simulation region is simulated by the following two sections. This is section 1 and section 2. In the first part, we obtain the macroscopic parameter rho, and then here the Zhu-He boundary condition is applied to the cells located in the left inlet in the grid to obtain the unknown population components. Then the collision formula is used to update the cell state after collision. So, as discussed in the lecture, to update the boundary cells in inlet, we first obtain the local density, and after that we use Zhu-He boundary condition to obtain the unknown component F1, F5, and F8, and after that we are able to use the collision equation as we discussed in week 7 to update the inlet boundary cells. Finally, after a normal streaming step, this piece of code implements an open boundary condition at the outlet of the flow. The open boundary condition is another type of boundary conditions which we didn't go through in the lecture. This boundary condition is employed in outlet boundaries to update cell states. Anyway, you know, like inlet boundary conditions, we need another kind of rules to update the cell states in outlet cells. Anyway, we use in this simulation, we use open boundary condition to update the state of cells located in the outlet of the grid. Okay, so in this implementation, we have inlet boundary conditions, we have bounce back or no slip boundary condition, and we have open boundary conditions in outflow condition. Okay. Now let's elaborate on the goal of this physics lab. As explained earlier, today we want to employ lattice Boltzmann models to simulate the lift and drag forces on aircraft wings. We simulate how the velocity of fluid particles, which represents molecules in the air, move through the air when these particles face an aerofoil or wing as an obstacle. So if you run the simulation code, we will see a kind of obstacle like an aircraft wing. And then, using lattice Boltzmann model, we simulate the fluid dynamics, and based on this simulation, we will compute the drag and the lift forces produced by this wing. We use NACA model to simulate the airfoil or wing shape in the grid. We need an obstacle. We need a wing shape obstacle. So to implement or to simulate this wing shape obstacle in the grid, we use this NACA model. The detail of this model is explained in this Wikipedia article. Every detail about this model and how we can compute the shape of a wing is explained in this article. Here, as we can see, the function NACA4415 computes the shape of an airfoil obstacle or a wing. In this function, let's go to the code. Yeah. In this function, we invoke another function named YT, as we can see here. The function YT, we have its definition here, calculates the profile of a symmetrical aerofoil with no camber or arc. So if you look at this shape, we can see here we have some symmetrical airfoil with no camber or arc. So, like for instance here at the start point. Then the function YC, which is defined here, is called. In this function, the symmetrical shape computed by YT is bent around a camber curve that is normally convex upward to yield a more traditional looking aerofoil. So as we can see here, we start with a very simple shape, And then by calling YC function, we can simulate a wing shape model, or we can obtain a wing shape obstacle. As we can see here, the obstacle function calls NACA4415 function to simulate a horizontal airfoil obstacle. But in real simulations, the airfoil or the wing needs to be tilted into the income flow by an angle of attack. As we can see here, and the wing shape here is horizontal. But you know, in real implementation and or in real simulations, we need to somehow rotate this wing or make it tilted. To do this, we apply a rotation matrix to the airfoil calculated by this function to obtain a more realistic wing shape. So as you can see here, we have we define alpha as angle of attack in degrees. Then based on this alpha, we rotate the shape of wing by alpha degree. Here in this function, we apply a rotation matrix to this shape computed by this function. Rotation matrix is something like this. For instance, here if we set theta equal to 30, the shape, the input shape will rotate by 30 degrees. So as you can see here, each point in the shape is multiplied by this rotational matrix, and the output shape will be a shape which is rotated by 30 degrees. So here in this code, if we set alpha degree equal to 30, it means that we want to rotate the wing shape by 30 degrees. We will use this code in the simulation code. As you can see here, the obstacle function here. We use NACA4415 function to simulate the shape of wing, and then we use this rotational matrix to rotate or to tilt the simulated wing. You can play with this attack degree or angle of attack to rotate the shape of wing. Okay, after understanding this code, please run the airfoil code as provided to observe how the simulation works. As the code runs, it will print out drag and lift forces produced by the wing. So you will see two numbers printed out by the simulation application. The first number represents the the drag force, and the other one is lift force. This is the forces produced by the wing. So these forces make these forces anyway, control the movement of airplane. The code initially has an angle of attack equal to 0. As you can see here, alpha is equal to 0. Please modify the alpha parameter value and study how this change the drag and lift forces. So you can, I don't know, for instance, one time run the code with alpha equal to 0. And then you can increase the value of this alpha and see how the drag and the lift forces change. Then you can use a negative value here. I don't know, for instance, minus 45, and see how the drag and the lift forces change. You can also play with, here we have, Reynolds number, and study its impact on the drag and lift forces. So you can decrease the value of this number, and even you can increase the value of this Reynolds number. As I explained in the lecture, if you set this Reynolds number to values greater than 1000, the simulation will be unstable. So you can see this practically in today's lab.